that gives you information on the chemical groups in the structure. If you have only aliphatic protons or protons on carbon close to heteroatom and so on. The second information is the surface under the peak that is proportional to the number of protons. We saw that on this molecule. The bigger the signal is, the bigger the number of protons under the peak and so we have information about is it a methyl group, a CH2 or whatever. And the third information we can get on on proton NMR spectrum is the number of line, what we call the multiplicity of each signal for each group of proton, which gives us information about what happened around, close around, in the neighborhood of the methyl group, for example. So depending on the number of lines, we will be able to know how many protons there are around, on the carbon around this group of protons. So we were just, we saw just the relationship between the multiplicity, that means the number of lines, and the number of proton in the neighborhood, and what we call equivalent protons. Okay. N equal the number of equivalent nuclei or protons, let's say, around, just around the proton, because we are talking about scalar coupling. That means coupling interaction, magnetic interaction between protons, but transmitted through the chemical bonds, through the electrons movement. And if we saw that also, we saw that starting with no protons on the carbons just aside, N equals 0 because there is no proton on this carbon, then the multiplicity M equal 1. That means I have only one line. This is called the singlet. If we have one proton on the carbon aside, beside, the protons here will have a resonance with two lines, multiplicity equal 2 because N equal 1. This is called a doublet. And you see here the integration equal 1. That means that I have here 1 protons. And here also I have 1 protons because I have 1 protons on the carbon beside. I didn't say that, but you see when we goes from this molecule to this one, if you have a doublet here, that means that I must have 1 protons on the carbon beside. I should see the same signals for the other protons. That means I have 2 protons in the molecule. Each of them are different because they have chemical groups, different chemical groups around. So they are submitted to different kind of interference because of electronegativity of each chemical groups. I have different frequency of resonance. But as they are close together, they are on two carbons side by side, then each of them has a multiplicity as a doublet. This one has one proton in his neighborhood, so he is a doublet, and the other one has only one proton on his neighborhood, so he is also a doublet. If we go on and we add another proton on the structure, you see that if we consider the aldehyde proton, we see that this proton has or is submitted to the interference of two other protons, so n equal 2, and the multiplicity is a triplet. That means that I have 3 lines. And on the other side, the two protons here, they have the same kind of environment, so they are called equivalent. And as they are equivalent, they have the same frequency of resonance, but the intensity of the signals or the surface under the peak is twice bigger than the first one. So I have an integration corresponding to 2 protons. And as these group of protons are coupling with only one proton, for them n equal 1, so they have a signal as a doublet. So in these signals, we have a triplet corresponding to a proton which is coupled to 2 equivalent proton. And on the other side, I have a signals as a doublet for 2 protons that are equivalent. And it is a doublet because they are coupled to only 1 proton. And if we go further, if this time I have a methyl group here, that means 3 equivalent protons on the carbon beside the carbon wearing the aldehyde group. The aldehyde protons is coupled to n equals 3 equivalent proton. The signal is then called a quartet. That means that I have 4 lines. 4 lines. And on the other side, the 3 protons that are equivalent in a methyl group, they have the same frequency of resonance. And as they are coupled to only 1 proton here, they have a multiplicity as a doublet. But the surface under the peak is 3 times higher than the surface under the peak of the aldehyde group, because here I have 3 protons with the same frequency of resonance, because they have the same chemical environment in the structure. So the integration is equal to 3. Okay with that? And if you look closer, you see that in a signal, when we have multiplicity, the lines, we can measure the distance between the lines. And this distance is calculated in Hertz, and it is called the coupling constant. And the value of the coupling constant will give us information on the distance that separate the 2 groups of protons. We see just before that we are talking about scalar coupling. That means coupling through the chemical bonds. So here, this value, I can measure it here in this picture, but I know that this value corresponds to the strength of the coupling between the two groups of protons. So this is called the coupling constant. So just go back to the multiplicity to understand, as you could see, well, sorry, just come back a little bit. Now we will try to understand why in a doublet the two lines has the same height. In a triplet, I have a big one in the middle and two smaller on the side. And the quartet is like that, a small one, two big, and a small one again. So we're gonna try to understand how we can anticipate this shape. And these signals are called a triplet and a quartet because they have this shape. If I have four lines with equal height, this will not be called a quartet. It's something else and it means something else. We will see that a little bit later. So what happened when we have coupling? So let's consider that the multiplicity equal n, the number of equivalent proton on the neighborhood beside, plus 1. Excuse me. So you know the Pascal triangle? I don't know. This is the Pascal triangle where the first column you have only one number for each column, and the first one you have only one. In the second, you start in the second from the second line, and then you write 1, 2, 3, 4, 5. The third column you start from the third line, and then the number is calculated from the first line. Here, for example, is 1 plus 0, so equal 1. 1 plus 1 equal 2. 1 plus 2 equal 3. 1 plus 3 equal 4, and so on. So in the third line, you do the same. 1 plus 0 equal 1. 2 plus 1 equal 3. 3 plus 3 equals 6. 4 plus 6 equals 10. And then this is how you build the Pascal triangle. So how can we use it to anticipate the height of the lines in the signal? Now we are going to see that. We will use the column, but we use it in the horizontal way. This rectangle show us the number of lines. I have 1, 2, 3 lines, and the number inside will give us the proportion between the line. The first one it has a proportion of 1. The second is twice high than the first one, and the third one is equal to 1. That means it has the same height than the first one. If I have a quartet, now I have 4 lines, 1, 2, 3, 4. And the proportion between the high is 1 for the first line. That means it's small. In the middle, I have 2 lines that are 3 times higher than the first one. And the fourth line is equal to the first, and so on. So that's why I call this a triplet, that one a quartet, because of the proportion between these lines. Try to move this a little. Okay, this is what I said already. So if I have only one proton, no proton aside, that means that I have a singlet. If I have one proton aside, I have a doublet, 2 lines with the same high. If I have 2 protons in the neighborhood, I will have 3 lines, and the second in the middle is twice higher than the one on the side. If I have 3 protons on the neighborhood, I will have 4 lines, and the 2 lines in the middle are 3 times higher than the one on the side. So how to use and calculate the coupling constant in the signals? Here you have 2 doublets. If you look at the chemical shift, we are up to 6 ppm. These might be double bond protons on double bond or in aromatic ring, because we are close to 1. Here you have in red the lines for the integration. You can see that the integration is calculated from here to here. And the computer said that this surface corresponds to 1 proton. And for that one, it's the same. The integration is calculated from here to here. It's very broad, and it corresponds also to 1 proton. And if we use only the lines here, the curves, we measure the high here compared to that one. And we can say that both are the same. So we have the same number of proton in both signals. Okay, so we use the chemical shift, we use the integration, and now we see that we have 2 lines in both signals. We can say that in the neighborhood of both of them, I have only 1 proton. 1 proton coupling to that one, and another proton may be coupling to that one, or the same coupling to both of them, but I have only 1 interference in the neighborhood. So how to use now the coupling constant? That means the distance between the lines in one signal. You see that this one is bigger than in this signal. So what does it mean? And how calculate precisely the value of the coupling constant? Remember, the scale here is the first scale in hertz, in frequency. That's why we call frequency of resonance. So for each line, I can ask the computer to give me the value of the frequency of resonance of each line. So the computer can write here the frequency of resonance of for each line. This is written in red here, so we can see 2,719, for example, for this line, 2,711 for that line, and so on. But to calculate the coupling constant, as we use the frequency, we can make the difference directly. The coupling constant in this signal will be the difference between this frequency and this frequency. We make the difference. This number minus this number, and this will, as these numbers are in hertz, I will have the coupling constant in hertz directly. But sometimes on the, sorry if it's noisy, I'm at the university and we are close to the hospital, and we have some
It's okay. There was no problem.
But most often, we have not we don't have the frequency here. We have only the value for each line, but in ppm. That means it gives the chemical shift for each lines. So then you need to make also the difference between the highest and the minus. You make this one minus that one. But as we are in a chemical shift, we need to add or to use to enter the value of the B0 field. Remember, it's the power of the machine. And here, for example, it's a machine of 300 megahertz. So then to have the value in hertz, we have to make the difference between chemical shift in ppm cross B0 and the divided by 10 power 6, because it's in megahertz here, and we want a value in hertz. So that's how we calculate the coupling constant. And as I said, the coupling constant will give us the strengthness of the coupling between the proton, and this strength is closely related to the distance between protons. So without the real value, but I can see that this coupling constant will be lower than that one. So that means that the proton that couple with this proton might be a little bit far away than for this proton, because the value is bigger. So we'll make some exercise and you will understand, I hope. As we have table for the chemical shift values, we have also table for the coupling constants that can help us to understand in which kind of distance we have. So it depends on the type of the molecule or the chemical groups. If we are in aliphatic molecules, we usually can see coupling through 2 or 3 bonds. I try to write, but it doesn't work. I don't know why it doesn't work here. I can't write. I don't know why. Sur le pointeur stylet. Ah. Okay. So J2, it's written like that. That means it's a coupling constant through two bonds. That means that the protons are on the same carbon. J3, it's what we play with until now. That means that we have two carbons side by side and we have two protons on one proton of each of them. So the protons are far away from three chemical bonds. 1, 2, 3. That's why we use 3 here. J4 means that I have, for example, something like that, and I have one proton here and the other one is here. 1, 2, 3, 4 chemical bonds separating each proton. So as you could see, here they are close, here a little bit far away, and here far away. So as the distance between the group of the protons, the smaller became the chemical shift. For example, for G equal to, just forget about the sign here. The value, the absolute value is around 12 Hertz. It's very high for a coupling constant. Most often we have J3 in aliphatic protons. In aliphatic molecule, it's around 7 to 9 Hertz. And for example, when you have allylic system like that, you have coupling between this one and this one, then the coupling is very small. It's less than 2 Hertz because the protons are far away one to another. And this coupling is observed because of the presence of the double bond here. We'll see that later. So I hope that you understand that the bigger the distance is between the proton, the lower the coupling constant will be. It's just like in love. Okay. In ethylenic molecule, let's say, if I could write somewhere here. You have two cases because you have two stereochemistry in a double bond. You can have a double bond in trans configuration or in cis configuration. Okay, so the value of the coupling constant will be different in each molecule. And that's important because we will be able, just in measuring the coupling constant, we will be able to say we have a trans configuration or a cis configuration. Even if both of them are J3 coupling constant. It's because of the double bond and the magnetic field between both protons. So I won't detail that. But what you have to keep in mind are the value. So if you have a cis double bond, the coupling constant is around 12 usually. So between 10 and 15. And if you have a trans configuration, it's around 16, 17. It's between 15 and 12. So it's very big. So when you have a big coupling constant like that, you must think about a double bond. And the value of the double bond, the limit is 15. If it's lower than 15, you have a cis configuration. If you are upper 16, you have a trans configuration. And then if you are in aromatic ring, remember the chemical shift is from 6.5 to 8, 9 ppm. You can also have coupling in an aromatic ring, just me draw. Okay, let's say we look at this proton and the change of the shape of the multiplicity of this proton depending on the number of proton on the aromatic ring. If I have no other proton here, what will be the signal of this proton? Can you tell me? Please, can you answer? One of you? I don't know.
Can you repeat the question?
If on the aromatic ring here I have no other proton, what will be the shape, the multiplicity of this proton? If I have only, let's say, an OH, only groups, chemical groups with no protons on this position. For example, this molecule, what will be the shape of the signals of this? How calculating the multiplicity? Remember, it's n plus 1. That means that n is the number of protons in the neighborhood. How many protons in the neighborhood you have? That means protons on carbon close to this proton.
0.
Yeah. So what is the multiplicity?
So the multiplicity is uh, 2.
No, if n equals 0, you told me that
So equals, so it is 1.
Yeah. So if the multiplicity is 1, how it is called? How is called the signal? We have something like that with only one line. That's what it means. So how do you call this? The name. It is a singlet.
So,
Okay. So if there is no protons around this one, n equals 0, so m, the multiplicity equal 1. That means that this proton will have the shape of a singlet. Okay, for everyone?
okay.
If now on the neighborhood I have 1 protons, and let's say that here I have another C. So what will be the shape of the red, the proton in red, if I have a proton here? So the question is, what is the value for n in this case? In this molecule, how many protons do you have? On the aromatic ring, I don't talk about these other protons, okay? I talk about the protons on the aromatic rings. Is there anyone here?
The proton here is also position.
Yeah. So how many proton do you have on ortho position?
So we have 1 proton on the ortho
Yeah.
position.
So m equal to
1.
and
So
yeah.
2 and
So we have a doublet, 2 lines. Yeah. And it looks like that. Always for the red protons, okay?
okay.
And now if I change again, if I add a proton here, what happened for the red one?
So n will equal 2,
Mm-hmm.
and then we'll have a triplet signal.
Yeah. Let me just change this. We will talk about that later. So, okay, we have 2 protons, but what is important to see also here, so n equal 2, is that the distance, because in an aromatic ring, the distance are fixed. The distance between each of them is exactly the same. Here we have a J3, and here we have a J3. We have a planar molecule. So we can say that as we have 2 protons in the neighborhood, the multiplicity will be 3. So the red proton will be a triplet. Okay? A triplet means that the lines in the middle is twice high than the 2 lines on each side. And the chemical shift is in the middle line. And the distance here is the same as here. That means that the coupling constant with the blue one is equal to the coupling constant to the green one. Okay? Because the value of the constant is the same, we have a triplet. Even if the protons are not equivalent, because the chemical shift around are not the same. So the blue one will have his own chemical shift, and the green one also. Let's say delta 1, and for the blue one, delta 2. So on the spectrum, I will have 3 different signals. The chemical shift for the red, the chemical shift for the green, the chemical shift for the blue. But the red one is coupled to 2 protons that have the same complete constant, so I will have a triplet. Okay? So after that, I have exercise. So what we can do is to just let me see a little bit far away. Okay. Let me add just a white page, and we'll try to do something together. Okay. Do you see the page? The white page?
Yes.
Okay. So, how is build? Because we didn't see that. If I just come back a little bit, if there is no proton aside, sorry, I have only one line, n equal 0. If in the neighborhood I have one proton, I will have 2 lines. Okay, the distance between both will give me the value of the coupling constant, and I will have the information on the distance between the proton. If I have 2 protons in the neighborhood that are equivalent or that has the same coupling constant, I will have a triplet. Something like that. Which means here I have the high equal 1 and this one equal 2. This is a triplet. Okay? So to understand why I can say that this value, this coupling constant equal to that one, I'm going to show you where the triplet comes from. So we can we can do that on here. I will change the color. So to find a doublet, the lines of the single is divided by 2 because I have one proton in the neighborhood. And for the triplet, each line will be divided again by 2. But as I have the same coupling constant, the first one will be divided with the same coupling constant as that one, and the second one again with the same coupling constant. In the middle, I will have a superposition of 2 lines, so that's why the high here is twice the high in the side. Okay? And if we have a quartet, we go on again. We have 3 times the same coupling constant, and you will see that in the middle, you will have superposition of one line of an intensity of 2 and one line of 1. That means that you will have a signal with 4 lines with the intensity of 1, 3, 3, 1. Okay? So why did I want to do that? Yes, it's because, so this is real if the proton in the neighborhood are equivalent. They are the same, they have the same chemical environment, or the coupling constant are the same. So that's why in the aromatic ring we just drew before, okay. So I can have one here and another one here. Here I have substituent. I don't have any protons here. So the black one will be a triplet because the coupling constant here is equal to that one. Okay? But now, if I draw, I hope I will. Sorry, excuse me. Allô? Ouais, je peux pas te répondre là, je suis en cours avec le Vietnam jusqu'à 11 heures. Ok. Salut. Excuse me. So if we just and now if I draw the proton here on this position, what will happen? What will be the shape of the black proton? Allô? Do you think that the coupling constant, the red coupling constant, will be the same as the blue one?
I think they have a different coupling constant.
Yes, because you don't have the same distance between each proton. Here you have a J4, and for the red one, it's a J3. Okay, for everyone. And we know that if the distance is bigger, the coupling constant is weaker. So we know that J3 will be bigger than the J4. I should write in blue, okay? And the value, we know with the table, the value of J3 in aromatic ring is between 7 to 9 hertz. And for the J4 in aromatic ring, is between 1 to 3 hertz. It's usually 2 hertz. Okay? So what will be the shape now, the multiplicity of the black proton? So we can do the same as we did on the draw on the left side of the slide. Just we can go on the other side. That means if we are here with n equals 0, I have only one line. Now, if n equal 1, I said that I have 2 lines. Okay? And if n equal 2, but here, even if it's protons, I said I have 2 J value. I have a big one and a small one. I will not have a triplet like before. Each line will be divided in 2, but with a smaller coupling constant. So I will have something like that. Always the chemical shift in the middle. And I will have something like that. Okay, for all of you.
Okay.
I would like to change the color. So the first will be the coupling with the big coupling constant. So here I can calculate the J3. Okay. And if I calculate the distance here, I will have the J4. And I can calculate here also, it's the same value. And for that, each line has been divided by 2. But the value is small, so I have no superposition of the line. So I can't have triplet or quartet or whatever you want. Okay? So here the signal is not called, even if I have 4 lines, I cannot call that a quartet because each line has the same height. So this is called a double doublet. Sorry. Double doublet. D'accord? Okay. And this is because these protons are, even if they are aromatic protons, they are not equivalent. They don't have the same chemical environment. That means that here I have a substituent, here I have another one, and here maybe another one. I have no symmetry in the molecule. So these protons, these three protons will have a different chemical shift, and also the value of the coupling constant are different. Can you tell me what will be the shape of the red one? If I do the same, so here, if I have the coupling with the black protons, it's a J3, so it's a big coupling constant, 8 Hertz. So I have something like that. I'm sorry, I can't draw properly. If n equal to, it's the same. It will be divided by 2 each line, but the distance between the red and the blue one is again weaker, is very big, as we have how many chemical bonds do I have between these two protons? 1, 2, 3, 4, 5. This is a J5. In aromatic ring, it is called J para. J3 is ortho. J4 is the metacoupling. And the J5 is again smaller than the J4, and it's less than 1 hertz, usually less than 2 hertz. Around 1 hertz or maybe less, okay? So its lines will be divided here by 2, but with a very small distance between them. Okay, here you will have the coupling with the black one. And this J3 should be equal to this J3, not on my draw, but it should be. Okay, in the middle. And then each line will be divided by 2, but this time with a very small coupling constant, which is calculated here, and we will have a J5. And usually we say that the J5 is difficult to calculate because the resolution of the spectrum usually is not high enough. So we don't see the para-coupling usually. But in theory, we should observe it, okay? So when you have a double doublet, so this is also a double doublet, but as you could see, the shape is not the same. Here I have, where is it? J3 and J ortho and J para. Here I have J ortho and J meta. We will see how to calculate this, the coupling constant. In a double doublet, I should have 2 coupling constants. Let's say J1 and J para and J ortho, let's say that. How can I calculate it? If we say that here the frequency of resonance of the first line is called nu1, nu2, nu3, and nu4, or that one, this one, this one, and this one. The J para, I said it's the small coupling constant here will be equal to nu1 minus nu2. And I can calculate it also with nu3 minus nu4. But the J ortho, as you could see, it's the big one, and I can find it here between this line and this line, or between this line and this line. So the J3, the J ortho will be calculated like this, nu1 minus nu3. But it is also equal to nu2 minus nu4. Okay for you?
Okay.
And here in the triplet, it's the same as we will calculate, as we have the same J, it will be nu1 minus nu2, and it's equal to nu2 minus nu3, because the distance here is equal to that one. Okay? So be careful about that, because your coupling constant will be wrong if you don't choose the right peaks. Okay. So we can do an exercise on this. What time is it? Do you want to make a small stop before we go on?
Thank you.
Okay, so 5 minutes, okay? Hello? Are you back?
Yes.
Yeah? Okay, so let's go to another exercise. So I don't know if you have take some time to look at this. What can you tell me on this spectrum? You just tell me and I write. Okay, so here you have the scale of the chemical shifts. What can you tell me? This is the solvent, the reference, so don't care about that. So what can you tell about the number of different group of protons? That means that I have to work again. Okay, if you count, I have one. Let's, well, when you have broad signal like that, usually it's about hydrogen of alcohol groups. So let's this apart for the moment. So I have 1, 2, 3, 4, 5, 6, 7, and don't forget this one. We have also other maybe protons on oxygen like that, but they are very de-shielded. So we will try to understand why. So you have another one. Yeah. Okay. Looking at the chemical shift, what can we say? Whatever, from which part you start is not very important. So we have something less than 3.5. So this might be something, a proton on a double bond. And we have signals over than 6.5. So these might be aromatic protons. Okay. But as this proton, as you could see, is a doublet. So I have to find somewhere in the spectrum his friend with the same coupling constant. So at the moment, it's difficult to say because the scale is too broad and we don't see clearly. But we'll see that on the next slide. So let's say like that. These are aromatic proton. Here we have a CH of the double bond. What about this and these are solvent? We are here in DMSO. So don't take care about that, and this one also. And what is interesting is these signals, you could see it's very high. And if we check the integration, I see that all these signals are for one proton, each of them. And here I have 3 protons. Okay, so this might be a CH CH3 group. But remember, we used to say that in aliphatic, methyl group is around here, depending on the position in the molecule. But here we are very deshielded compared to this standard value. We are around 3.8 ppm. And this corresponds to methoxyl group on aromatic ring. So we have different elements here. We know that we have an aromatic ring. We have a double bond. We'll calculate the coupling constant in a moment. We have a methoxyl group on the aromatic ring, and we have either acid, carboxylic acid protons or alcohol protons on aromatic ring. So at this point, this is only what we can say from this spectrum. Here, just in the parameters, you see they give the solvent here. What do we have also? This is the temperature, and this is the value of B0. We have a 400 megahertz machine. Okay. So here is the broad part of this part from 6.4 ppm until 7.6. So just like that. Here we have the proton at 3.8 ppm. The integration said it's 3 protons, so I confirm that this is a CH3. The chemical shifts told me that it's methyl close to an oxygen and on an aromatic ring. What is the shape of the signal? How it is called? This signal is a singlet. Okay, we used to say we have a CH3 with the chemical shift 3.82. This is a singlet. This is how it is described. And what about the other part of the spectrum? We talk about this first signal, which is a doublet with the chemical shift here just in the middle. So it's a 6.31235 ppm. And so it's a doublet. Can you calculate the coupling constant, please? So this is nu1 and nu2. Remember, here you have the value in hertz. So can you calculate the coupling constant, please? Are you sleeping over there?
No, I'm here.
Oh, it's difficult for me to teach like that.
I'm sorry.
No, it's not your fault. It's because of the COVID and so on. Okay, so I calculate it's 15.8 hertz. So I remember I told you if a proton has a multiplicity, that means he has an interaction with another proton, and I should find in the spectrum is another signal with the same coupling constant. If I check here, it's not here, it's not here, but I have something quite the same here. If I calculate the coupling here, what is the value? I also have a doublet. Um, 20. It's the same. 15.8, nearly 9. So that means that this proton, let's say it's proton A and proton B. We know that these two protons with a chemical shift of 78, A and B are on the same double bond. Okay, as the coupling is around 16, that means that I have a trans double bond. Say A and B. I don't know yet what are here and here. Okay. What about the three other signals here? So we are between 6.7, well, over 6.5 and over 7. So these might be in an aromatic ring, these three. And why can I say that they are on the same ring? It's because of the coupling constant. I see that all of them are at least a doublet or more. Here I have 4 lines and they have quite the same height. So here I have a double doublet. Here I have a doublet and here also a doublet. So I know that I have something like that. And on this ring, I have to place 3 protons on this aromatic ring. And what will help me is the value of the coupling constant. Here, if I calculate the coupling constant, I found here I have 1.9. And if I calculate, I will find the same value here and the same value here. And the big one is 2.6. 8.2. That means the big one here is 8.2. Remember, the small one is calculated here. I find it again here and here. And the J3 will be calculated from here to here, or from here to here. Okay? So 8.2 is an orthocoupling. 1.9 is a metacoupling. This is a trans coupling. And if I calculate the coupling constant in the last signals here, I will find again a value around 8.2 hertz. So because I have the same kind of coupling between these three protons, that means that they are on the same ring. So if I put here the proton here, which is a doublet ortho, this is it. Where should I place the other two protons? Say the double doublet will be orange, and the other one will be red. So the double doublet means that it is coupled in ortho with the first proton. So that means that in position ortho, I will write the orange, which is the double doublet. As the blue one doesn't couple to the third one, we can't measure the coupling constant with this one. So then remember I said that even in 400 megahertz, it's hard to see the paracoupling, but the red one, which is the doublet meta, is in meta position from the orange. So I have a meta coupling here and an ortho coupling here. And between this one and this one, I have no coupling because it's a J5 and it's a little bit too far to be observed and measured. And here the blue one has only one coupling observed or measurable. It's the ortho coupling. Okay, for all of you?
Okay.
Any question? No?
No for me.
Okay. So what about on this ring? I have three other positions. where there is no protons because I don't have it there. I know that in this, for the substituent, I should have a double bond. I should have a O-methyl group. And remember, on the proton here, I have these two signals, which could be OH group. If I check the table here at 12, usually it's something like that, carboxyl group, OH from carboxyl group. And here in the table, I will see that usually it's OH on aromatic ring. So now I will have many possibilities to write or to put these substituents. I can draw whatever I want. I mean, here I can put the OH, here the OCH3, and here the double bond. Sorry. I can write this, but up to now, I have no idea if this is the right structure or not, because I could put the double bond on another place. Same for the CH3. So at this point, I can propose many structure, at least 3 different structure for this molecule. And what will help me to choose which one is the best one, it is to consider the value now, the value of the chemical shift of each group, because this value is directly linked to the electronegativity of the substituent on the next carbon, for example. So we will not do that today. So this is the same spectrum, but with the calculated by the computer. It's not the observed one. And here is the final structure and the good one. And you can see that here the OH of the carboxyl group is around 12. Here are the 2 double bond, the ethylenic protons with the coupling constant of 15. You have here the 3 protons and the other chemical groups. And these values also are theoretical value, and as you could see, quite close of what we have observed. Here, just an example to show you how the measuring the coupling constant could be very interesting. We saw that in double bond, it will help us to see if determine the configuration of the double bond, either it is cis or trans double bond. But even in aliphatic molecules, when you have racemic, not racemic, asymmetric carbons, you have here, for example, you have 4 asymmetric carbon, and it's the same down. You see that depending on the orientation of the position alpha or beta of the substituent, you will not have the same shape of each signals. This depends on the orientation in space between the protons. So the calculation of the J3 will be very helpful to say if we have a proton in beta position or in alpha position compared to another, depending on the value of the coupling constant. Here, as you could see, this is a double doublet with a small coupling constant and a bigger one. Here you have another one with, again, a double doublet, but a little bit different because the coupling constant here is a little bit broader than here. And here you have a doublet and another doublet. And if you check here, this proton here, you have no proton, you have only one here. So this will be a doublet. It's the same for that one, but as they are, the environment, chemical environment is quite the same, so they are very close together. But as you could see, the orientation of the proton here and here are not the same, so the coupling constant will not be the same in both signal. You have a small one and another one bigger. And the other two protons, let's say the triangle, if I can draw like that. Each of them is coupled to one and a second proton, so they are coupled to two protons. The orientation are different, so the coupling constant will not be the same. And then we have doublet for each of them. And here, this molecule is quite the same. The only thing that changed is the orientation of the protons. That means that here the proton is in the front. Here it was in the back. And here, again, the proton is in the front. And here it's in the front and so on. So as you could see, the value of the coupling constant are not the same, and we are able, just measuring these coupling constant, we will be able to choose between these two structures, even if the structure, the crude formula is quite the same. So it's very important to understand what the coupling constant means and how we can calculate it when we have different kind of signals. So as an example, again, what is important to see or observe in order to be able to say if we, for example, when I have a coupling with two protons, the question is, are they the same? Same or same coupling constant, or are they different? This is the big question. So when you have the structure, it's easier, of course. For example, here in this molecule, this is a methyl with a bromine. In a methyl group, the three protons are always equivalent. They are always the same. So we always have only one chemical shift for all of them, and they will not couple one to another because they are all the same. There is no difference. Here in this molecule, for example, so these one are equivalent. I will have only one chemical shift with an integration corresponding to 3 protons on this molecule. And these two, as we have no asymmetry in the structure, then they will be said or called equivalent. So we will say that they are the same. So they will have the same delta. So we will have one chemical shift for that one and a second one for both of them. We will have an integration for 2 protons. And as they are close together, here we have a J3, then we will observe a multiplicity. Here, for both of them, it's the same signal. They are coupled to 3 protons, so the multiplicity will be 3 plus 1 equal 4. As they are the same here, we'll say that we have a quartet here for this delta 2. And for delta 1, the methyl is coupled to 2 equivalent protons, so M equal 2 plus 1 equal 3. And I have a triplet because I have the same distance and the two here are equivalent. Okay, so in the spectrum, I will have a triplet here and a quartet here. A triplet bigger because I have 3 protons and here I have only 2. For this other molecule, I have 2 CH2 in the molecule, but one is close to a carboxyl group, another one close to a methyl. So even if the 2 protons of one CH2 are equivalent, they will have one chemical shift here. These blue are equivalent, so they will have a second chemical shift because the chemical environment is different. So here I will have 2 protons and for the integration, each of them. Here I have 3 protons, so I will have a third chemical shift for 3 protons. And if I check the multiplicity, for the blue one, I have coupling with 2 protons, which are the same distance, same chemical shift. So the multiplicity M equal to 2 equivalent, same distance, same chemical shift. So I will have a triplet. For the red one, I have the reciprocity of the triplet here. So I will have coupling with 2 equivalent protons, which will give me a triplet. But on the other side, I have a coupling with 3 equivalent protons. So these 3 will give a quartet. So I should have theoretically a quartet triplet or triple quartet. You can write this also. So it's very complex signal for that one. In theory, okay. In practice, it will be a little bit simpler because you have only J3. And in an aliphatic system, all J3 are quite the same. So it's just like if the red one are coupled to 3 plus 2, that means 5 protons. M equal as J are the same. 5 plus 1 equals 6, I have a sextet. Sextuplet in French, sextet in English. Okay, and in aromatic ring, it's simpler because what I need to check is do I have any proton on the aromatic ring, on the carbon of the aromatic ring? If I don't, here I have a carbon, but remember I have double bonds, so here I don't have any proton. Here I have, and here I don't have any proton, which say that we have quaternary carbons here. So when if I'm able to see an axis of symmetry, then I can say that these two protons, the blue one, are equivalent. I will have only one chemical shift integrated for two protons for the blue one, and for the red one I have the same. They are the same, so I have a second chemical shift integrating for two protons. But as the red one has a chemical shift different from the blue one, they are coupling one to another, and as I have it's just like I have only one half of the molecule, just forget that one, because it's the same. Everything is twice. I mean, this signal counter for two protons, the red one also, and I have the coupling only with one proton on the side, so each of them will be a doublet. So on the spectrum, I will have one doublet for the red one, another doublet for the blue one, and I can measure an orthocoupling, each of them integrating for two protons. Okay.
Okay.
Maybe we can stop here for today, and in the next slide you have some exercise. Maybe you can try to do that for next time. And next time will be on Monday, right? No. Yes. Is that okay for you?
It's okay.
So let me check only how many exercises I have afterward. Maybe you can do these two exercises. Here you have some other slide for about what we talked today. Ouais. Je vais conserver ça. Just check what kind of exercise I will give you. Well, you can do these two exercises for this molecule and that one, and maybe in the other document training. Did I send you this document? Sorry, just show you. I don't remember. Did I send you this exercise? Well, I check. I will send you some. Yes, I did. I remember now. So you will prepare this exercise called the file called training Proton and J in PDF, and the two exercise we saw in the lecture. Is that okay for you?